These are the expressions for the rate constant for a second order reaction. Now this is the natural logarithm, which generally is log to the base e. And this is log to the base 10, which is the general logarithm form that we all know. Now the question is, how are these equations being derived? How can we come about them? And how were they brought? Now, these are equations that are derived in a situation where there is a reaction between two different reactants. Let us say A and B, which basically leads to the product, no matter how many the products might be. So that is what this video is all about. We want to see how these equations could be derived. So let's jump right into it. And the first thing you need to know is that if two reactants react, let's say A and B, it will basically form products. Okay, now A is the reactant A, I should just say, and B is basically the second reactant. Now A would normally have a molar concentration and B would also have a molar concentration. Now you could represent the molar concentration of A as A written in square brackets, and this might well stand. So basically we are talking about the molar concentration of the reactant A and the molar concentration of the reactant B. Now we actually need to write this stuff in its rate law form. So how can we write that? If you wanted to write the rate law for this chemical reaction, this is basically how it's going to be written. Now let me start from the most basic form. If you had just one reactant undergoing a chemical reaction to form a product, the rate law for this, so let us write that. The rate law for this will be negative d a dt, and this will be equal to Ka. Now, the reason why there is a negative here is as a result of the fact that the reactant A would actually reduce over time. So as the products form, the reactant reduces in its concentration, or whichever quantity that is under analysis at that time. Now K here actually stands for the rate constant. You could also call it the specific velocity constant for the chemical reaction. Now if you do not want to write the K in that place, it could also be written this way. So you would have negative dA dt, and this will be O. So I really need to write the proportionality sign. So this is what we're going to have. Okay. So let me make the dt to look better. So this will be the rate law for this reaction involving only one reactant. And so if I wanted to remove the proportionality sign, I'm actually going to introduce an equal to sign with a constant, which is going to be basically this equation. Now, in this case, we are actually dealing with two reactants. So how can we write the rate law for that one? This is how it's going to be written. So I'm going to take the first reactant and write the rate law for it. So this is going to be negative dA. And we have dt. Now I will take B and also write for it. So that is going to be equal to negative dB. So I need to write dB in square brackets to represent the molar concentration that is involved. So this will basically be proportional to the concentration of A. And take note, A actually is just 1 mole, so we're actually just going to write 1 on top as the power of the concentration of A. These terms are actually called concentration terms. Then we have B. So B is also raised to the power of 1. So if I wanted to remove this proportionality sign, this is going to be negative dA dt, and this will be equal to negative, well, this is dB, this is going to be dt. Now this will be equal to k. And so I could just write a without the powers, because that is basically b to the first power. Now, this is going to be the rate law for this reaction in its initial form. So let me just indicate that in blue. Now, you need to know something. Now, if reactions actually take place, they would always need time to occur. So if you have a reaction occurring, you actually need to measure the time over which that reaction proceeds. So if a reaction begins, it's actually going to have some of the reactants eaten away from the left hand side and being formed on the right hand side as another product, as a chemical change. Now, before the reaction takes place, there would actually be no product on the right hand side of the reaction. Now, there is actually a rate law for that. In a situation where you do not actually have any product forming on the right hand side, that is actually the situation where time is equal to 0. So t will be equal to 0 at that time. And that actually happens to be this rate law. So this rate law, I think I might just write it here. This is the rate law for this chemical reaction in a time where there is actually no reaction taking place. And we know that because the time is actually equal to 0. So there is actually no reaction taking place here. Now, this is what you need to know. If you have a reaction before occurring, it's actually possible to write the rate law for that reaction. And so basically, this is the rate law for this reaction in a time where there is no reaction taking place. So time will be equal to 0. Now, I just need to rewrite this and show you some other stuff. Now, we need to write this in another form because it's actually very possible for you to have this written in another form. So what you need to know is that this is the initial concentration of the reactant A. Of the reactant A. Okay, so I'm just going to write A there. And you also have a B in square bracket, which is also basically the initial concentration of the reactant of B. Now, this is called initial concentration because at this time, we do not really have a change or a reduction in the amount of the reactants A and B. So this would actually be called the concentrations at time equal to 0. Now, that is so because there would actually be no reduction. There will be actually no reduction or decrease in the amount or the concentration or the volume or the pressure, whichever quantity that you are actually using for the analysis of that reaction. So there will be no reduction. And the rate law for that is exactly what we have actually shown here. Okay, this one. Now, you could also write the initial concentrations of the reactants A and B as this. You could also write A to be written as A naught. You could write it as A naught, or you could write it as a small a. Now, B could also be written in the same form. So this will be B, and that is B naught, and then this is going to be B generally. So if I wanted to write the final amount of the concentration of the reactant, which would actually be at a time where some reaction has taken place, so time would at that time not be equal to 0. It's actually going to be equal to some value that is greater than 0, obviously, because time would have passed, and so some reactions should have occurred, right? So if you wanted to write that one, that will be written as, if you wanted to use this, you could use this, and this will be a final. For the small letter, we could use a minus x to represent the fact that the amount remaining was actually coming from a reduction of some amount from the initial concentration. Now you could also write for b to be b final. And if you do not want to write it this way, you could write it as, I think I just need to wipe that out. So this could also be written as b minus x. Now this is at situations where t is equal to some value. Now since we do not know exactly what the value of t will be, let us just write it as t. But we know that it must be greater than 0, because if it is greater than 0, then it actually means time has passed. And if time has passed, as far as you combine these two reactants, there must be a reaction, because it has been studied and it's proven that some reaction should take place there. Right? Now, having got that, let us go back. So first off, we have the equation of reaction written as some a plus b, and that will yield some products. Now, we know that at time t equal to 0, that is the time when no reaction has occurred. And so the rate law will be written this way. So the rate law will be written as negative d a dt, and this will be the same thing as negative db, and that will be dt. And so this is going to be equal to k into a and into b. Now, after some time t, so t will be some value which we might not actually be able to tell now, but at least we know that some reaction has occurred since time has passed, right? So we know that these initial concentrations would reduce, right? So the initial concentration, which is A, will reduce by some value x, which we do not really know what that x is, but we know that this will be the final concentration. So if this is the initial, this will be the final. And this is actually reasonable because you have some value x going away from the initial concentration. So what will remain would actually be the final stuff, which is A minus x. So this could also be called the final concentration or the remaining concentration for the reactant. And the same thing holds for B. If you had B to be the initial, then the final or the remaining amount will be after some amount x has left after some time t, and that will be the final amount or the remaining amount. So what I'm actually going to do, excuse me, what I'm actually going to do is replace A by A minus x. So that will be the amount. So basically you're going to have something like this. This will be A minus x, something like this, and you would also have b minus x. So this is equal to some value. So let us say this is x coming from A, and this is also x coming from B. So here we have some product on this side. For the time t equal to 0, we did not actually have anything, so that would basically have been up 0. Nothing formed because no reaction has occurred. Time hasn't spent. Okay, so this is what we have. Now we could also write the rate law for it. So let us try to write that. So this is going to be rate law, and so it will be written as a negative d, and then you have a minus x dt, and this will be the same thing as minus d of b minus x, and this will be dt. Then on this side we're going to have k into a minus x also, and then we also have b minus x, so I think I just need to use the space here. Yeah, so that is what we're going to have. Now you should know that it's possible for me to expand this stuff. So basically it will look this way. You're going to have a negative dA. Now if I use negative to differentiate this stuff, or rather I should just say let us use negative d to FOIL these brackets. So if I multiply negative d by a, that should give us negative dA. And if I multiply negative d by negative x, that will basically give me dx. This whole stuff will be over dt. Now for the second term, we have a negative dB plus dx. This will be over dt. Then on this side, we have k will be equal to, will multiply by a minus x and b minus x. So this will be the rate law for the second step, where t is equal to t, right, after some time. Now, this was actually gotten from the method that is used to represent the rate law for equations. Now you need to know that for forward reactions, if I just had A and this proceeded to the product, the forward reaction would have a rate law that would only involve the reactant. So no product is actually involved in the rate law equation. So that is the reason why you do not see XA or XB being formed on this other side. It's basically just going to be everything that you have on the left hand side. That is the reactant side. So that is basically how to write the rate law for a reaction, which is just a forward reaction. So this is a forward reaction. Now, we need to work some stuff here. Now, you need to know that I could actually split this stuff and make it this way. So this would actually be minus dA dt. And this would be plus dx dt. Now, this is equal to negative dB dt and plus dx dt. This is equal to k into a minus x multiplied by b minus x. Now, you need to know something. We said that A was the initial concentration of the reactant A, right? And we said it was the initial concentration because time was equal to 0. Now, if time is equal to 0, that means there was no time spent, right? Now, if no time was spent, then what that means is that A did not change, right? And so if stuff doesn't change, what that basically means is that the stuff will be a constant, right? So for every quantity where the value of t is equal to 0, that quantity is basically gonna be a constant. So A is actually a constant in this case, since we do not have it actually changing. B would also be a constant because it's actually the initial concentration for the reactant B. This is for the reactant A, and B is the initial concentration for the reactant B. So in that case, since we have this stuff written from the beginning as T equal to 0, that is, there are actually quantities which are there when the time is equal to 0. And that means that they are actually constants because they do not have no change happening with them. So they're basically going to be called constants. So if that is the case, what will happen here is we have a change in a constant with respect to t. So that is going to be basically 0. If you differentiate a constant, that basically should give you 0. So this will be a 0. And this is actually not a constant. This is a variable, some value x that got reduced away from the initial concentration. We do not actually know what that is. That is the reason why it is actually designated as x. And for the b, we also have x for the b. So that means this will cancel out and this will cancel out because their derivatives would be equal to 0. So this will be dx dt, and this is equal to dx dt, which is actually reasonable. Dx dt is the same thing as dx dt. So on the right hand side, what we have is k multiplied by a minus x, which is also multiplied by b minus x. So I could basically just use 1. So the new equation that we have is dx dt. And this is equal to k into a minus x and into b minus x, basically. So this will be our new equation at time t equal to t. Now you need to know that this actually occurred because time is equal to t. That is, we have some amount of time that has actually been spent in this reaction. So this will be the new equation. Now this is the equation which we actually need to integrate. So basically, I could take dt and multiply it to the right hand side. So that will give me dx, and this is going to be k multiplied by dt, and this will be multiplied by a minus x, and this is also multiplied by b minus x. So what I'm going to do in the next step is to take a minus x and b minus x away from this side and take it to this other side so that I will integrate them with respect to x. Now, how can I do that? That is basically by dividing through by a minus x and b minus x. So this is going to be b minus x. And obviously, on this side, I also need to write a minus x and b minus x. So this would cancel out. So we would have a new set of sides of terms. So that gives us dx divided by a minus x, and this is b minus x. Then this will be equal to k dt. So let us call this equation 1. Now what we need to do is to integrate equation 1 at upper limits and lower limits. So I just need to wipe some stuff out. So this is integrating at the upper, and I'm going to write lower limits. And that is basically what we call definite integration. So what should be the upper limit for this one? And what should be the lower limits? Now we have integrations basically occurring in a situation where you have the variables present there. So we have a variable x. So the upper limit obviously for the variable x should basically be x. And the variable x in the lower limit will be 0. Now why is that? That is actually occurring because we know that from the beginning we had the initial concentration where there was no value x. So that was basically 0, and that was at the time where time was equal to 0. So there was no reduction in the amount of the initial concentration. So x was basically 0. Now after some time we had some amount x being real and numerical, right? So it's actually going to be the highest value. We do not know what that value will be, but at least we know that the highest will be at some value x and the lowest will be 0. So 0 will be the lower limits and x will be the upper limit. Now that goes for the same t, because in this case we find that t is the stuff that is changing. This is dt, change in t. So upper limit will be t, and the lower limit should be 0 basically. So with that, we're going to have something like this. So this will be x, and this is going to be 0. So I have 1 divided by this stuff. So this is b minus x, and this is multiplied by dx. And on this side, we have our t, and we have 0. So this will be k dt. Now, the problem here is how to do this one. So in order to solve this, you actually need to use the formula of our partial fractions. So we need to understand how to do this with partial fractions. So this is what you need to know. If you had something this way, let's say if you had 1 divided by a minus x. Sorry, wow, that should be x. So let me write x there. And then this is b minus x. If you had this, you could actually split this into partial fractions. That will be written as a divided by the first stuff, which is a minus x. And that will be added to one stuff, which should be on top, and divided by b minus x. Now, for now, we do not know what a or b is. So what you need to do is to find out. So if we find out, then we could replace this stuff with these expressions which are written on the right hand side of the equation, because that will be better, and we would actually integrate both terms of these results. So let us see how that will be. Now I could just wipe this out. So we need to solve this. Now how can we solve this? How can we find the values of a and b? So what we need to do is to multiply both sides with the denominator which is present on the left hand side, which is a minus x and b minus x. So this should be a minus x and this is our b minus x. So this is what we're going to do. If you use this stuff and multiplied it by this should basically cancel out, because that is going to be 1 divided by a minus x, b minus x, and this will be equal to, well, that should rather be multiplied. So this is multiplied by a minus x, b minus x. Now obviously these should cancel out and just leave a 1 there. So that is basically what we're going to do. So in this place we know that this cancels out. And so we just have 1 sticking out there on the left hand side. Now for this one, we're going to use this and multiply by this first term on the right hand side. So that is going to cancel a minus x with this one, right? So that will leave only b minus x, which would multiply with a. And so that is supposed to be a multiplied by b minus x, right? Then we have b minus x multiplied by this stuff. So this is going to cancel out with this one, and that will basically leave a minus x, okay? Now a minus x should multiply with b. So this is going to give us b multiplied by a minus x. So this is basically what you have. Now the next thing I need to do is I could just assume that that x should be equal to a. If I made x equal to a, that is going to cause this to eliminate out, and that will leave only the variable of a left for me there. So let us try to do that. So this is going to be a multiplied by b. So this is b minus a, and this is going to be plus b into a minus a, which this cancels out because this will be 0. And 0 multiplied by b, that is going to be 0. So this basically is just what we're going to have. And so this makes a to be 1 divided by b minus a, right? Now this is what you have. So let us try solving for b. Let's try to see what b would be. Okay, so how can I find b? Now I need to eliminate out this term. The only way that I can do that is to make x to be b. That is a small case b. So this will be b. So if that is going to be the case, then we're actually going to have 1, and this will be a into b minus b. And here we're going to have a minus b. So this obviously will cancel out, and so we're just going to have 1, and that will be equal to b multiplied by a minus b. So I could find what b is by making it the subject. So that makes b to be 1 divided by a minus b. So that is what you have for b. Now we have gotten these two terms. So we can now substitute them back into the original expression. So I'm just going to wipe this stuff out and clear these ones out. Okay. Okay. Yeah. So we know what A is and we know what B is. So that means this is going to be 1 over B minus A divided by A minus X. And this is plus 1 over A minus B divided by B minus X. So that is basically what you have. Now I could take this stuff down as well as this one. So let us see what that's going to give us. That is going to give us something like this. That will be 1 divided by B minus A. And this is into A minus X. This will be plus 1 divided by A minus B. This is going to be B minus X. So this is what we have. What that means is this stuff, this is what it is equal to. So we need to replace this with this ones. So let us do that. Now we know that initially we had the integral sign with a dx there. Now this whole stuff has been changed to this. So we need to change it. So we are actually going to have integral. We have 1 over b minus a. And this is a minus x. And this is plus 1 divided by a minus b. And we have b minus x. And so this is dx. And on this other side, remember we had k dt, integral k dt. Now what we need to do in the next step here is actually to split the integral sign over each term inside of the expression. Now if I did this, this is going to be integral 1 divided by b minus a. And this will be a minus x. And this will be, I think I'm going to have a dx, so that should be there. So both this and this would actually be used to FOIL the brackets. Now this is going to be 1 divided by a minus b, and this will be b minus x. We also need to have dx there. So this will be integral. You have a k dt. Now this is what you need to know. I could actually change this to look like this. Now how can I basically do that? If I multiply this stuff with -1, that is going to change this. Or I could actually just factor out -1 from here. So how can I do that? If I have, let us do it this way. So this is minus a. So if I factor out -1 from here, that should be a minus b. Then if I factor out -1 here, that should be a plus a. So this is going to be -1. Now rewriting this, this should be a, well, that is minus b, and we would actually have a minus outside. If I use the minus and FOIL the brackets, that will basically take me back to the original stuff that we have here. So I just want to make it to look more homogeneous with what is on the other side or on the second term of the integral. So that is what I'm going to do. Now this will make it to be integral. I could actually write it this way because I actually do not want to waste too much time. So let me make it to minus. So this will be a minus b, and this will be a minus x, and you have dx here, and this will be integral 1 over a minus b. So as you can see, we have been able to change this stuff. And the negative, which was supposed to be here, that is the one that we have taken outside, because that will basically be a -1, which is a constant. So this is dx. We need to write b minus x here. This is integral k dt. So now this is what we have. So I could actually take some stuff out, right? Now before I do that, let me factor out some stuff here. So before doing that, let me rewrite it. Let me make integral 1 divided by a minus b into b minus x dx, and this will be minus, I'm gonna write this one. So you have this is a minus x. So this is dt, and this is equal to integral k dt. So this is what you have. Now, as you know, a was a constant, b also was a constant. So I could actually factor out that stuff. Stuff seems very long, isn't it? We actually need to do it. So this is integral 1 over b minus x dx. This will be minus integral 1 over a minus x, right? And we have a dx. Well, so this should actually be a dx. So I need to rewrite this one. This is also a dx. And on this side, I have integral k dt. So that is what we have. Now, stuff is actually very long in it. Well, you need to just pay very close attention and be a little bit more patient. We'll soon find the stuff. Okay, so the next thing we need to do now is to integrate the stuff. Okay, so let us see how that is going to be. Now remember, we were to integrate this at upper limit of x and lower limit of 0. So I just need to write that here. And for this other side, we needed to have it as t, and this also 0. Okay, now if I integrated this, you know that the integral of 1 over x should basically be ln x. Now you need to divide it by the value of the derivative of the function there. As far as the function is a linear function, you can actually differentiate it, and you'll be able to add it to the answer. So we know that the derivative of x is basically 1. So what if you didn't have this one? What if you had integral 1 over b minus x? Now b is a constant. So we know that this should be ln b minus x, but then we need to divide it by the derivative of b minus x. The derivative of b should give us 0. The derivative of minus x should basically give us minus 1. So that is what we're going to do. So let us see what that gives. So this is going to be 1 over a minus b, and this will be, I think I'm going to use this one. Yeah, something like this. So this will be minus ln, and this will be b minus x, right? And so this actually needs to be at the upper limits of x and lower limits of 0. And on this side, we have a minus with the answer, which should still be negative ln, and this is going to be a minus x, right? And this will be x and 0. Yeah. Then for this one, we know that this is a constant, so basically it's not really going to get integrated. It will just go outside and stay here. So we just need to integrate dt, which basically should give us t. Now t will be at upper limit of t and lower limit of 0. We're almost there. Stuff is actually very long. Now, we need to evaluate what these values are going to be. So how do we do that? Now, first of all, we need to know what is meant anytime you have something like this. Let's say you have a b or a minus x, and this is raised to the power of x, and let's say raised to, I said raised to, that is actually supposed to be of the upper limit of x, and let's say there is a y here. So you could actually change it. This is going to be a minus x. So what I actually did was I used the x and substituted it as x in the first case. Then the next thing you need to do is to subtract it by this substitution of y as x. So the variables which are actually given, would get substituted by the upper limits and the lower limits. So that is a basic thing that we need to do. So for this one, we're going to have something this way. So this is what we have. Now this is at the upper limit of x and lower limit of 0. So this will be minus ln. First of all, I have b minus x. And then I have minus this stuff again, which is going to be ln b minus 0. Now why is this so? So I used x to substitute into this stuff. So by doing that, I actually had x because x is x. So if I substituted x into x, that will basically be x, right? So that is going to give us a b minus x. And remember, we had a negative here. Then we also have minus, which is actually supposed to be the case because anytime you're doing this, you actually need to subtract for definite integrals. So this will be minus ln b minus 0. Now b minus 0 basically is going to give us b, right? So this makes stuff to become this way. This is ln, we have b minus x. And this will be plus what? Ln b, right? So this is actually what we have. Now if you have two logarithms added together, basically what that means is they would actually get multiplied, right? They would actually get multiplied. So this should be, this is not actually a multiplication because we have a negative here. So this is how it's going to be. This is going to be ln b, and this will be minus ln b minus x. So this is what we have. Now, if you had this, this will be changed to ln, and you have b divided by b minus x. So this is basically what you're going to have. So for this part, what we have is this. So I'm just going to go put it there. So let us go there. So this is into ln b over b minus x. So this is what you have. So I'm just going to place it there. And then we need to go to this other one. So this will be minus. Now we need to work with this one. So let's see what that's going to give. Right. So I have x to be substituted as x. And so if I did that, that should give me minus ln. I got a minus x because x is substituted as x. So that basically would still give us x. Then we have minus the other stuff, which will be ln a minus 0, since we have 0 to be the lower limits. Now, if you do not really know how to solve questions for definite integrals, you could just check out my channel because you would actually really need to have a good understanding of what definite integrals are to be able to know really what I'm doing in this place. So let us go back. Now this is going to be negative ln a minus x, and this will be plus, right? So this is going to be plus, and we have ln a, right? So I could actually change this to look rather this way. So this is what I have. Now, if you had such a representation, it's easy. This would actually be changed to ln a, and that will be divided by a minus x from the law of common logarithm basis. Well, so this is what we have, right? Now, I need to plug this here, so I'm going to plug that there. So let me wipe this and rewrite it closer here. I could just write it this way. So this is ln, and we have a divided by a minus x. Now this is what you have. And on this other side, we're just going to have k into t, which is actually the substitution of the variable t in the first case as upper limit. And that will be minus the substitution of 0, which basically should give us 0, right? So this is what you have. Now, we are inching very close to the end of the derivation. Now, what are we going to do with this stuff? So this is what you need to know, right? If you have ln A minus ln B, that should basically be ln A divided by B, right? So I'm going to use that method here. Now that will make this stuff to be 1 divided by A minus B, and this is going to be ln. So I actually have B divided by B minus X, and this will be divided by what? A divided by A minus X. So this is what I'm going to have. I think I could redraw this. So let's make this to be this. So this will be T minus 0, which gives us a T. Now I will just represent the K, in this case to be K sub 2, just to show that we're actually dealing with the specific rate constant for a second order reaction. So we know that this stuff could actually change to a multiplication, and that would cause a switching, a reciprocation of this fraction, right? So this is going to be ln, and we're going to have B divided by B minus X. I need to bracket this, and this will be multiplied by A minus X, right? And this will be divided by A. And this is equal to K to T, right? So we're actually getting very close to the end of the stuff. So let me write K2 or K sub 2T on this side, and let us write this on this other side. So this is going to be A minus X. Now for this one, we have ln B multiplied by this is basically going to give us B into A minus X, right? Then we have also B minus X multiplied by A, which is going to give us A into B minus X. So this is what you have, right? Now this is equal to this. So this is actually the answer to, we might not actually say that this is the answer yet. Let's see what that's going to be. Let's go on. So I need to take T away from this stuff. I need to make it to be a denominator, or I just need to divide both sides or multiply through by 1 over T. Let me just multiply through by 1 over T. So this will be 1 over T. So this cancels this out, and this gives us K2. Then on this side, I could multiply A minus B with T. So that is going to give us 1 divided by, I have A. Well, so this should be A minus B, and this is T, right? And this is going to be ln. So I have B into A minus X, and this is divided by A into B minus X. So this is what we have. So this is actually the representation of the rate constant for a second order reaction. Now, as you can remember very closely, we actually also had another one where ln was actually changed to log to the base 10, and we had a 2.303 there. So how can we do that? How can we find that one? So that is going to be the next focus now.